In this podcast, we're going to look at the low mass stars and what evolutionary path they follow. Better start the actual presentation. So, by low mass stars, we're referring to M, G, K, F, and A, probably, on the main sequence, the stellar classes. And all these stars start the same. They all start with the hydrogen burning converting to helium. The definition of a main sequence star, apart from its position on a HR diagram, is that the hydrogen burning into helium is basically the fuel source. That's what's going on. Hydrostatic equilibrium is being maintained by the gas pressure pushing outwards and the gravity pulling inwards. Very low mass stars, which are often referred to as red dwarfs, have a mass of between just under 10% to about 50% the mass of our Sun. Because they are so low mass, they have very, very low luminosity, which means that they use up fuel very efficiently. They use it at a very low rate. An additional feature of low mass stars, red dwarfs, is that they are completely convective. So hydrogen burning occurs in the core, because that's the only place with the density and pressure required. But the products of that burning, the helium, is mixed in with the rest of the star, and this also means that the hydrogen in the whole star can be recycled and brought back into the core and made sure that it's used so that all of the star is available as a fuel source. So these two properties taken together mean that red dwarfs have exceptionally long lifetimes on the main sequence. For a very low mass star, say 20% of the Sun's mass, it has a projected lifetime of about 1 trillion years. 1 times 10 to the 12 years. Stars with a little bit more mass, approximately the mass of our Sun, from about half a solar mass up to, say, 4 solar masses. They have much shorter lifespans on the main sequence, but still pretty lengthy, up to 10 billion years, or maybe a bit more. Our Sun will be up to about 10 billion years. Now, red dwarfs, I said, were wholly convective, but yellow dwarfs have a defined central core, which is where the nuclear fusion takes place, and the heat from that core is transferred via a radiative layer to the convection areas in the envelope above. The consequence of this is that only hydrogen in the core is available for fusion into helium. Our Sun will never use most of the hydrogen it has. What goes on in the core stays in the core. Only elements present in the core can be fused, and the products of those reactions will also remain in the core. Over the course of the Sun's lifetime on the main sequence, it doesn't stay in the same place exactly. Instead, it will drift upwards and rightwards. Over time, it will become slightly more luminous. It will get slightly bigger, which means that the outside layers, despite the increased luminosity, will get slightly redder and cooler. After a while, however, helium will build up in the core, and the hydrogen burning will move from the core itself, in the middle of the core, through to a shell around the core. This has a couple of effects. It means that the rate of energy production actually goes up, because it means it's increased pressure because it's squeezed between the outer layers of the core and the helium, the inert helium core. This gives energy to the envelope, which makes it expand, which makes it cooler. And this moves it on to being a red giant, in the initial red giant phase of the part of the Hertzsprung-Russell diagram. The helium doesn't itself start fusing for a while, but for any star above half the mass of our Sun, it can reach the conditions required for helium fusion. That moment when helium fusion first occurs is called the helium flash, and when that occurs, the star maintains a large amount of luminosity, but it actually shrinks in size. It becomes a bit more of a stable burning regime, and this is known as the horizontal branch, and it lasts for quite a while. A star can spend up to 1 billion years on this horizontal branch as a giant star. However, again, over time, the helium will start being consumed. An inert core of carbon and oxygen will build up by the triple alpha process, and the helium fusion continues again in a shell around the core, with hydrogen fusion still continuing above that. The effect of pushing this hydrogen fusion out further into towards the envelope and the helium beneath it is to significantly increase both the luminosity and the size, which will result in a decrease in the surface temperature of the star. This is known as the asymptotic branch of the red giant, and this is as large as the star will get. And that's pretty large. The Sun as a main sequence star is about 0.01 astronomical units in diameter. The Sun as a red giant has a diameter of over 2 astronomical units. That's twice the distance potentially from the Sun to the Earth in its current orbit. So these stars are pretty darn big. One of the closest examples of one of those is a star called Mira, and you can see a picture of it where optical interferometry techniques have been used to produce an actual image of the star, not as a point source, but as an extended source. And extended is actually the right term to use with Mira. It is noticeably non-spherical. And part of the process, part of the reason for this, is that these large stars, they're not gentle. They're not happy giants. Instead, they have extremely strong stellar winds, which are getting rid of significant amounts of mass on an annual basis, about 1/1,000,000th of the star's mass per year, which may not sound like much, but don't forget this is a process that happens over hundreds of thousands of years, whereas our Sun currently loses a trillionth or less of its mass due to the current solar wind. Another consequence is that these stars are often very variable. We've already looked at Cepheid variables, and this is a similar process. Cepheid variables are inherently much more massive, and it's also a lot less regular, so we can't use it as a standard candle. But the magnitude can change significantly in waves and pulses. And both of these effects combine to get rid of much of the envelope of the star. Because it's so large, the gravity at the surface of the star is very, very weak, and it doesn't take very much energy for the particles that make up the envelope to reach escape velocity from the star. So that combination of the thermal pulses from the variable star and the strong solar wind or stellar wind mean that it loses its material out into the interstellar medium, and this can be seen in the photograph here at the bottom, which is taken using ultraviolet light. This strange sort of comet-like picture actually shows that star Mira and nearby area of space. And the reason for that appearance is that the star is actually moving relative to the interstellar medium and quite fast. From our perspective in this diagram, it's moving from left to right. And so that very strong stellar wind pushes up against the interstellar medium, creating the bow shock that you see on the right. The bow shock that you see on the right, and this long trail of material that has come from the star itself. Eventually, pretty much all of the outer layers will suffer mass loss. The ejected material spreads out into a planetary nebula, as can be seen in the photograph behind this slide. The planetary nebula actually gets energy from the exposed core, which is giving off very, very hot. So the radiation it gives off is ultraviolet. That is true all the time. It's just that normally by the time that radiation passes through the outer layers and reaches the photosphere and makes its way to us, it's been reduced down to the visible. But that very strong ultraviolet light excites the gases present in the planetary nebula and makes it glow these quite pretty colours. The core itself now dies. Temperature isn't required. It's not able to fuse carbon and nitrogen and oxygen. The helium that's left and the hydrogen that's left is not enough to sustain nuclear fusion. And so very quickly the star fades. We don't know that we've ever seen a star actually undergo this process because It happens very, very quickly. And we are left behind with a white dwarf. The white dwarf is the exposed core of a dead star. It's white because it's hot. It's hot because it started hot. It's not actually generating any radiation, or sorry, it's not generating any heat itself. There's no nuclear fusion going on. So it's gradually getting cooler and cooler. It's very small because the lack of fusion means that there's no longer any thermal radiation pressure in order to balance gravity. So the gravity squeezes the exposed core, squeezes the white dwarf as hard as it can. And the only thing that stops it from collapsing further is the pressure of the electrons pushing on each other on the outer shell of the atoms. So this electron degeneracy pressure. The consequence of that is that a white dwarf might well have a mass up to or maybe slightly over the mass of our sun. In fact, the maximum mass that a white dwarf can have is just over 1.4 times the mass of our sun. Obviously, that mass will be somewhat less than the mass of the star that created it. I predict that our sun would create a white dwarf with a mass of half the mass of our sun. But whatever the mass is, it will be approximately the size of the Earth. In fact, interestingly enough, the more massive the white dwarf, the smaller it is, because the greater gravity there is squeezing the white dwarf. So the summary is hydrogen fusion on the main sequence. Over lifetime, it drifts up. It enters the red giant stage with fusion in the shell. Then helium kicks off with a helium flash into the horizontal phase, up to the asymptotic, hydrogen fusion in the shell, ejects the outer layers to form a planetary nebula, and then cools and fades to a white dwarf. Before I go, what is the evidence for this? And there's one piece of pretty cool evidence, and that comes from looking at globular clusters. Globular clusters are large clusters of 100,000 to 1,000,000 stars approximately, that were all formed approximately at the same time. And these clusters are found orbiting our galaxy. They're not actually inside the main body of the galaxy, which also means that they are internally consistent. Every star that you can see in this picture, apart from a couple of foreground stars, was basically born at the same time. And if we look at the Hertzsprung-Russell diagram and construct one for a globular cluster, it looks like this. The main sequence still exists, but it's truncated. Nothing exists in the top half of the main sequence. And that's because, as time has gone, the higher mass stars, which live much shorter lives, have all evolved into the next phase, and this continues over time. If we come back to this same globular cluster in a few million or billion years, then we'll see it has a similar shape, but again, the main sequence will occur down here. So these stars of this mass, which in other words have this luminosity, which in other words on the main sequence have this age, are now becoming the first subgiants, then they're becoming red giants, then the helium flash occurs, okay, and then they go down to the horizontal branch stars. They hang around here for maybe up to as much as 1 billion years before they head back off up the asymptotic branch, asymptotic branch. They do this, they're the biggest, largest stars in the cluster. They form planetary nebula, and then they very quickly collapse down to form white dwarfs. Using this information, you can both not only easily follow this evolutionary path, but by looking at where the turnoff is, it's a good way of judging the age of the globular cluster as well. Okay, thank you very much. Fascinating stuff.